So, here's something worth sitting with as you settle in tonight. Somewhere out there, maybe on the other side of the galaxy, maybe just across the room, there are pairs of particles that were born together, flung apart, and yet somehow still know things about each other instantly. Not eventually. Not after a signal has time to travel. Instantly. You measure one, and in that same moment, before any light could possibly have crossed the distance between them, the other one already knows what to be. Let's make that a little more physical before we go any further, because I want you to actually feel this, not just hear the words go by. Imagine two coins. Ordinary coins, except these two are special. You flip one in Tokyo and your friend flips the other in Buenos Aires. And no matter how far apart you are, no matter how randomly each of you flips, whenever you compare notes afterward, you find that they always land opposite. Heads and tails. Every single time. Not almost always. Always. And here's the strange part. The part that made one of the smartest men who ever lived spend the last 20 years of his life trying to prove it couldn't be true. Neither coin has actually decided which way it's going to land until the moment it's looked at. Not we don't know which way it'll land. Genuinely undecided. A real, measured, physical fact about the universe, not a metaphor, not a thought experiment dressed up to sound spooky. Physicists call this entanglement, and it broke Albert Einstein's brain so badly that he spent 2 decades of his life trying to find a crack in it. He never found one. The universe, as it turns out, really is built this way. You don't need any background in physics for tonight. You don't need to remember a single equation from school, if you ever learned any at all. All you need is a willingness to let a strange idea sit there for a while without immediately trying to force it into something familiar, because some of what we're about to talk about simply refuses to be made familiar, no matter how patiently you turn it over. That's all right. That's actually the whole point. Tonight we're going to walk through why that's true, slowly, without any rush at all. We're going to talk about why entanglement doesn't let you send messages faster than light, because that misconception has a way of nagging at people if it isn't cleared up early, and I don't want it sitting in the back of your mind while you're trying to drift off. And we're going to talk about how this strange, almost embarrassing feature of the universe, the thing Einstein dismissively called spooky action at a distance, has quietly become the operating principle behind real machines being built right now. Machines that encrypt messages, machines that move quantum information from one place to another, machines that might one day form a kind of quantum internet stretching across the planet and maybe beyond it. If you drift off somewhere in the middle of all this, that's completely fine. The ideas will still be here when you wake up. And honestly, some of this makes more sense when your mind is loose and unguarded anyway, when you're not trying so hard to force everything into tidy little boxes. So let's start gently, with a question that sounds almost too simple to matter. What does it mean for something to not have decided yet? Think about a coin sitting in your closed hand before you look at it. In your everyday experience, that coin already landed heads or tails the instant it stopped moving. You just don't know which one yet. Your ignorance is the only thing that's uncertain. The coin itself is perfectly definite. It's just hiding its answer from you. That feels obvious. It's how basically everything in your life behaves. The keys are either in your left pocket or your right pocket. You don't know which, but they're somewhere specific, sitting there quietly being exactly one thing, waiting for you to check. Quantum mechanics says that at the smallest scales, the universe doesn't play by that rule. This is called superposition, and it's worth sitting with for a moment before we go any further, because entanglement is really just superposition wearing a slightly different costume, superposition shared between two places instead of held in one. Here's the classic way physicists like to think about it, and you've probably heard some version of it before. Imagine firing tiny particles, electrons, say, one at a time, at a wall with 2 narrow slits cut into it, and behind that wall, a screen that lights up wherever a particle lands. If electrons behaved like tiny little bullets, the kind of solid, definite objects you're used to, you'd expect 2 bright bands on the screen, one behind each slit, because each electron would go through one slit or the other and land roughly behind it. That's not what happens. Instead, you get a whole pattern of stripes, bright and dark bands alternating across the screen, the unmistakable signature of a wave interfering with itself. As if each electron went through both slits at once and interfered with its own possibilities on the other side. And here's the part that should really give you pause. This happens even when you send the electrons through one at a time, with long gaps in between, so there's no way they're bumping into each other or coordinating somehow. Each single electron, alone, unbothered, still produces that same striped pattern once you fire enough of them. It's as though each individual electron, before it's measured, isn't traveling through one slit or the other. It's doing something more like exploring both possibilities simultaneously, a smeared-out wave of potential, and only when it hits the screen, only when it's actually measured, does it commit to one single, definite spot. This double-slit business, by the way, isn't some newfangled quantum trick invented in the 20th century. The basic experiment, using ordinary light instead of electrons, goes all the way back to 1801, when an English polymath named Thomas Young shone light through two narrow slits and watched it produce exactly this kind of striped interference pattern on a screen, proving, to most physicists' satisfaction at the time, that light was a wave, full stop. And it stayed settled that way for over a century, until Einstein came along in 1905 and showed that light also behaves, in certain experiments, like a stream of discrete little packets, particles we'd later call photons. So light was already living this strange double life, wave in one experiment, particle in another, decades before anyone thought to ask whether matter itself, electrons, atoms, might be hiding the same secret. It turned out matter hides exactly the same secret. Run the double-slit experiment with electrons instead of light, and you get the same striped pattern, the same evidence of a wave interfering with itself, even though electrons are supposed to be solid little particles with mass and charge, nothing at all like a rippling wave of light. A physicist named Max Born figured out how to make sense of this mathematically back in the 1920s. He said that the wave describing a particle, what's called the wave function, isn't a physical thing sloshing around like water. It's a wave of probability. Square the height of that wave at any point, and you get the likelihood of finding the particle there if you look. Before you look, the particle genuinely doesn't have one definite position. It has a whole landscape of possible positions, each with its own probability. The measurement isn't revealing a hidden fact that was already there. It's the moment the fact gets created. Take a slow breath with that idea for a second, because it's really the seed everything else tonight grows out of. In your everyday life, uncertainty is always just a stand-in for ignorance. A shuffled deck of cards has a definite order, you just don't know it yet. A locked door is definitely locked or definitely unlocked, you just haven't checked which. Quantum mechanics is telling you that at the smallest scales, some kinds of uncertainty aren't like that at all. They're not standing in for some hidden fact you could learn if only you were clever enough or had a good enough instrument. The fact itself doesn't exist yet. And once you've accepted that a single particle can be genuinely undetermined this way, entanglement is really just the next natural, if much stranger, step. What happens when two particles share one single undetermined story between them? A story that only resolves into something definite once, together, even though that once, together can be separated by an entire galaxy. Now, that idea alone is strange enough to keep you thinking for a good long while. But it's not tonight's main event. Tonight's main event is what happens when you take two particles and let them share a single, unified description like this, when their fates become woven together in a way that no distance can unravel. The man who really put a name to this phenomenon, who looked at it and said, essentially, this right here, this is the strangest and most important thing about the whole theory, was the Austrian physicist Erwin Schrödinger. Schrödinger is someone we've already met once before, in a way, if you've been following the long history of quantum mechanics generally, because it was Schrödinger who, back in 1926, worked out the elegant wave equation that describes how a quantum system evolves over time, the equation that lets physicists calculate exactly what that spreading, probability-carrying wave function actually looks like for any given situation. He was in his late 30s at the time, older than most of the other young revolutionaries who were reshaping physics in that era, and by most accounts a complicated, unconventional man in his personal life as much as in his physics. But by 1935, nearly a decade after his equation had already reshaped the field, Schrödinger found himself unsettled by something else entirely, a paper that had just crossed his desk from across the Atlantic, and it's that unsettled feeling that led him to coin the word we've been building toward. This was 1935, and Schrödinger had just read a paper that troubled him deeply, a paper we're going to spend some real time with in a few minutes. And in wrestling with what that paper implied, Schrödinger coined a word for it in his native German, Verschränkung, which gets translated into English as entanglement. And Schrödinger didn't treat this as some minor curiosity tucked away in a footnote. He called it the characteristic trait of quantum mechanics, the one feature that forces you to abandon, once and for all, any classical way of thinking about the world. To make the weirdness of entanglement land, to force people to actually reckon with it rather than wave it away, Schrödinger invented one of the most famous thought experiments in the history of science. You've almost certainly heard of it, even if you've never thought carefully about what it's actually doing. Schrödinger's cat. Here's the setup, and I want you to picture it slowly. A cat is sealed inside a box, along with a small amount of radioactive material, a Geiger counter to detect radioactive decay, and a sinister little mechanism. If the radioactive material decays, and remember, in quantum mechanics, whether or when an individual atom decays is genuinely undetermined until it's measured, then the Geiger counter clicks, which triggers a hammer, which breaks a vial of poison, which kills the cat. If the atom doesn't decay, nothing happens, and the cat goes on living undisturbed. Now here's Schrödinger's cruel little point. If you take quantum mechanics completely seriously, if the radioactive atom is in a superposition of having decayed and not having decayed until someone looks, then by extension, the whole chain of events connected to it, the counter, the hammer, the vial, and yes, the cat, should also be in a superposition. Not just uncertain to us, genuinely, physically undetermined. The cat, according to the strict logic of the theory, is simultaneously alive and dead until the box is opened and someone looks inside. Schrödinger wasn't proposing this because he thought cats could actually be both alive and dead at once. He found the idea absurd, and that was exactly his point. He was holding up a mirror to his colleagues and saying, "Look, if you really believe the equations the way you say you do, this is where they lead. And doesn't that strike you as a problem?" It's one of the great ironies of physics that this thought experiment, designed as a kind of reductio ad absurdum, surely this can't be right, became one of the most famous and most often misunderstood images in all of science, sometimes even cited as if it proves that quantum weirdness scales up to cats and coffee cups, when Schrödinger meant it exactly the opposite way, as a challenge, a provocation, a request for someone to explain where exactly the transition happens between the strange quantum world of atoms and the solid, definite world we actually live in. Modern physicists have a pretty good, if not entirely philosophically airtight, answer to that request, and it's worth pausing on for a moment, because it's exactly the reason you'll never actually open a box and find a cat that's genuinely, physically both alive and dead. The answer is called decoherence, and the basic idea is this. Keeping something in a delicate superposition, a genuine, undecided blend of two possibilities, requires that the thing be almost perfectly isolated from its surroundings. The moment it interacts, even slightly, with the vast surrounding environment, with stray air molecules bouncing off it, with photons of light scattering from its surface, with the trillions upon trillions of particles making up the rest of the world, that environment effectively performs an accidental, uncontrolled measurement, and the delicate superposition collapses into one definite outcome or the other. Incredibly quickly, far too quickly for anyone to ever catch it in the act. A single atom, carefully shielded in a laboratory, can be kept in superposition for a meaningful stretch of time, because it's genuinely possible to isolate one atom from the world. A cat, made of some 10 followed by 27 zeros atoms, all constantly jostling against air and light, and the box itself, decoheres so fast, essentially instantaneously, that there was never really any practical hope of the cat's own fate staying undetermined for any length of time a human observer could notice. So the cat was never the problem. The problem, the genuinely open one that decoherence only partly answers, is where exactly, at what precise scale, the line falls between systems small and isolated enough to hover in superposition and systems large and entangled with their surroundings enough that they don't. That's still, in its full philosophical depth, an active area of thought, even if the practical physics of why your cat is never actually in two states at once is by now extremely well understood. But Schrödinger didn't stop at one cat, because the paper that had prompted all of this, the paper that made him coin the word entanglement in the first place, wasn't really about a single system being uncertain. It was about two systems, far apart from each other, being uncertain together, in a coordinated, correlated way that seemed to violate everything physicists thought they understood about how information and influence move through space. So let's extend the cat thought experiment the way the real puzzle demands. Imagine two boxes, two cats, and imagine that the radioactive decay triggering each box's mechanism isn't independent. It's linked somehow, so that whatever happens to determine the fate of the first cat is bound up with what determines the fate of the second, even if you take those two boxes and separate them by 1,000 miles. That's the real puzzle. Not just one uncertain thing, but two uncertain things, correlated across space, in a way that seems to demand some kind of communication between them, and yet no communication, none at all, appears to actually be happening. It's worth noticing, too, how naturally this two-cat version of the thought experiment slides you toward a question that feels almost unavoidable once you're sitting with it. If cat number one's fate and cat number two's fate are somehow linked, correlated across 1,000 miles, then opening the first box and discovering, say, a very much alive cat, seems to instantly tell you something certain about the second box, still sealed, still 1,000 miles away. How could that possibly be true, unless some kind of influence, some kind of signal, has somehow leapt across that entire distance in no time at all? That question, stripped of its cats and its poison and its hammers, reduced down to its barest, most rigorous mathematical form, is exactly the question that had already been sitting on Schrödinger's desk a few months earlier, in a paper written not by him, but by three physicists working together on the other side of the ocean. And that brings us to the paper itself, the one that started this whole chapter of the story, published earlier in that same remarkable year, 1935, by three men whose initials would become permanently attached to it: Einstein, Podolsky, and Rosen. The EPR paper. Boris Podolsky and Nathan Rosen were both younger physicists working alongside Einstein at the Institute for Advanced Study in Princeton, New Jersey, where Einstein had settled after fleeing Nazi Germany 2 years earlier, in 1933. The paper the three of them produced together carried a title that reads almost like a direct challenge, a title daring you to disagree with its implied answer. Can quantum mechanical description of physical reality be considered complete? And the argument they built inside it, patient, careful, mathematically rigorous, was constructed to argue, forcefully, that the answer was no. Let's walk through their argument slowly, the way they built it, because it really is a beautiful piece of reasoning, even though, as we'll see, the universe ultimately said no to its conclusion. Picture a source that creates two particles together at the same moment, in the same event, and then sends them flying off in opposite directions. Because of how they were created, quantum mechanics predicts that certain properties of these two particles will always be correlated. Let's keep it simple and think about something like spin, a kind of intrinsic rotational property that particles carry, which can be measured along different axes and comes out as one of two values. Let's just call them up or down. Quantum mechanics says that if these two particles are entangled in a particular way, and you measure the spin of one particle and find it's up, then you know with total certainty, before you even check, that the other particle's spin, measured along the same axis, will come out down. Every single time. It's like our two coins that always land opposite. Except this correlation has been tested and confirmed experimentally more times than almost anything else in physics. Now here's where Einstein, Podolsky, and Rosen pressed hard on something that felt deeply uncomfortable. According to the standard interpretation of quantum mechanics, the one championed by Niels Bohr and known as the Copenhagen interpretation, neither particle has a definite spin before it's measured. The spin is genuinely undetermined, hovering in that same kind of superposition we talked about with the electron and the double slit. But then the moment you measure particle A and find its spin is up, you instantly know that particle B's spin is down, even if particle B is, in this thought experiment, on the far side of the galaxy. How does particle B find out what happened to particle A? How does information about the measurement get there, seemingly faster than any signal could possibly travel? The phrase itself, spooky action at a distance, actually comes from a private letter Einstein wrote a little later, in 1947, to his old friend and fellow physicist Max Born. the same Born who gave us the probability interpretation of the wave function we talked about a few minutes ago. Einstein and Born have been corresponding for decades, going back to their years together in Germany before Einstein fled the country in 1933. And in that particular letter, tucked into an otherwise ordinary exchange between two old friends, Einstein used the German phrase Spuckhaft Fernwirkung, spooky action at a distance, to describe exactly the kind of instantaneous correlation the EPR argument was built around. He did not mean it as a compliment. He thought it was absurd, a sign that something was missing from the theory, not a genuine feature of nature. And his proposed alternative was, on its face, wonderfully simple and intuitive. Suppose, he said, that both particles actually had definite spins the entire time, from the very moment they were created, and quantum mechanics just doesn't capture that information. It's not that the universe waits until you measure to decide. It's that the universe decided long ago, and our theory is simply incomplete, missing some deeper layer of description. Here's the analogy that makes this feel almost obvious, almost comforting even. Imagine you have a pair of gloves, a left glove and a right glove, and someone puts one glove in each of two identical boxes without telling you which is which, then mails one box to you and one box to a friend on the other side of the world. You open your box and find the left glove. Instantly, you know your friend's box contains the right glove. But there's nothing spooky happening here at all. No signal traveled between the boxes. The gloves were always left and right, from the moment they were packed. You just didn't know which was which until you looked. Einstein's argument was that entangled particles might work exactly like this. Not spooky correlation created at the moment of measurement, but ordinary correlation, baked in from the start, revealed rather than created. Einstein, Podolsky, and Rosen actually built their argument around a very precise, carefully worded criterion for what should count as a genuine, physically real property. They said, roughly, that if you can predict the value of some quantity with total certainty, without in any way disturbing the system you're predicting it for, then there must exist an element of physical reality corresponding to that quantity. It's a deliberately modest, careful-sounding condition, almost impossible to argue with on its face. And they pointed out that in the entangled pair we've been imagining, once you measure particle A and find its spin is up, you can predict, with total certainty and without laying a finger on particle B, that its spin will be down. By their own careful criterion, then, particle B's spin must already have been a real, definite element of physical reality all along, whether or not the equations of quantum mechanics happen to describe it. And since ordinary quantum mechanics insists that no such definite spin exists until measurement actually happens, the theory, they concluded, must simply be leaving something out. Incomplete, not wrong, but incomplete, missing some deeper layer that a fuller theory would eventually supply. This is called a local hidden variables theory, and it's worth unpacking those two words carefully because they matter enormously for everything that follows tonight. Local means that nothing can influence anything else faster than light can travel between them, which is a principle drawn directly from Einstein's own theory of relativity, a principle he held to with total conviction. Hidden variables means that particles carry real, definite properties all along, properties that existing quantum theory simply fails to describe, properties that are, in a sense, hidden from our equations even though they're really there, the way the identity of the glove in the box was really there, just hidden from you until you opened it. And underneath this technical argument sat something deeply personal for Einstein, a conviction about what reality itself is supposed to be. He believed, with real philosophical force, that things have definite properties whether or not anyone is observing them. There's a wonderful, slightly biting story about this. Einstein once asked a colleague, a physicist named Abraham Pius, whether Pius seriously believed that the moon exists only when he's looking at it. It sounds almost like a joke, but Einstein meant it with total sincerity, because that's precisely what the Copenhagen interpretation seemed to be implying about the tiny particles at the foundation of everything. If a particle's position or spin only becomes definite the instant it's measured, if measurement creates reality rather than revealing it, then in some strange sense, the moon really might not be fully there in any definite way when nobody's looking at it, at least not according to the strictest reading of the theory. Niels Bohr, the great Danish physicist who had become quantum mechanics' most passionate defender, responded to the EPR paper, and his response was long, careful, and by most accounts, more than a little difficult to follow even for other physicists at the time. But underneath the dense argumentation, Bohr's position was essentially this: you cannot separate the description of a quantum system from the entire experimental arrangement used to measure it. Asking what the particle's spin really was before measurement, independent of any measurement, is asking a question that simply doesn't have an answer because the question itself doesn't make sense within the framework of the theory. There's no hidden fact sitting there waiting to be uncovered, Bohr insisted, because fact, in the quantum world, only comes into being alongside a specific measurement, in a specific context. You can't peel the observer's role away from what's being observed and still be talking about the same thing. Bohr and Einstein had already spent years locked in this kind of argument, most famously at a series of gatherings in Brussels called the Solvay Conferences, funded by the Belgian industrialist Ernest Solvay, which brought together the era's most brilliant physicists for intense, invitation-only discussions. One of the most vivid examples of their sparring came at the 1930 Solvay Conference, several years before the EPR paper itself, but it captures the flavor of the whole ongoing argument perfectly. Einstein proposed a thought experiment involving a box filled with radiation, fitted with a clock-controlled shutter that could open for a precisely measured sliver of time, letting exactly one photon escape. By weighing the box carefully before and after the photon left, using his own equation relating mass and energy, you could work out exactly how much energy that single photon carried away. And since you also knew, with precision, exactly when the shutter had opened and closed, you'd seem to know both the timing and the energy of that photon with a sharpness that Heisenberg's uncertainty principle said should be impossible. For one evening, this one actually rattled Bohr. Colleagues who were there described him as genuinely distressed, pacing long into the night, unable to see where the trap lay. But by the following morning, he had it. And the way he found the flaw is one of those details in the history of physics that feels almost too perfectly ironic to be true. Bohr pointed out that weighing the box necessarily means letting it move very slightly in the Earth's gravitational field, and Einstein's own general theory of relativity says that a clock which shifts position in a gravitational field experiences a tiny corresponding shift in how it keeps time. Once you work through that shift carefully, it turns out to introduce exactly enough uncertainty into the timing of the shutter to preserve Heisenberg's principle after all. Einstein, in other words, had been defeated by his own theory of gravity, deployed against him by Bohr in defense of the very quantum mechanics Einstein was trying to unsettle. That was the pattern, breakfast to dinner, again and again, across these gatherings. Einstein would arrive with some clever new thought experiment designed to show that quantum mechanics permitted you to somehow violate its own rules, and Bohr would spend the entire day pacing and worrying over it, and by dinner, he would have found the flaw. Every single time. It became something of a ritual between two of the greatest minds of the century, one relentlessly probing for cracks, the other relentlessly patching them, and by all accounts neither man ever landed a knockout blow against the other's basic position. Einstein never found a logical contradiction in quantum mechanics. He just couldn't bring himself to accept what it seemed to be telling him about reality. And that unresolved discomfort is exactly the mood he and his two younger collaborators carried into the EPR paper 5 years later, an attempt not to show quantum mechanics was inconsistent, which Einstein now accepted he probably couldn't do, but to show, instead, that it must be leaving something out. And here's the remarkable, almost humbling thing about the EPR paper specifically. For nearly 30 years after it was published in 1935, it just sort of sat there. Most working physicists treated it as an interesting philosophical puzzle rather than something with any practical scientific consequence. You could be firmly on Einstein's side, believing deep down that hidden variables must exist, or firmly on Bohr's side, believing that measurement genuinely creates rather than reveals, and it didn't matter one bit for your day-to-day work as a physicist. The equations of quantum mechanics gave you exactly the same predictions either way. The debate felt, to most people, like a matter of taste, of philosophical temperament, rather than something you could actually go into a laboratory and test. There was one significant attempt during this quiet period to build a genuine alternative theory along Einstein's lines, and the story behind it is worth a moment, because it happened against a backdrop that had nothing to do with physics at all. In 1952, an American physicist named David Bohm developed a complete, mathematically rigorous version of quantum mechanics built explicitly around hidden variables, a theory that reproduces every single prediction of standard quantum mechanics, but does so by assuming that particles really do have definite positions at all times, guided along by an underlying wave. Bohm did much of this work under genuinely difficult circumstances. He had been swept up in the anti-communist hearings of the McCarthy era in the United States, called before Congress, and when he refused to testify against colleagues, he found himself effectively blacklisted, unable to keep his position at Princeton, and he eventually left the country altogether, first for Brazil and later for Britain, where he'd spend most of the rest of his career. It's a small, human detail worth sitting with for a moment, that one of the boldest, most rigorous attempts to rescue Einstein's picture of a definite, hidden variable universe was worked out by a man who had just been forced to leave his own country because of political suspicion and exiled, doing some of his most careful thinking about the deep nature of reality while building an entirely new life somewhere else. It's often called pilot wave theory, and it's a serious, respected piece of physics, one that some physicists still work on and champion today. But there's a catch, and the catch turns out to matter enormously for tonight's story. Bohm's theory only works if you give up locality. It requires that distant parts of a system can influence each other instantaneously, actual faster-than-light influence baked directly into the mathematics. So Bohm managed to save hidden variables, in a sense, exactly what Einstein wanted, but only by sacrificing the very thing Einstein held most sacred, the strict locality drawn from his own theory of relativity. It's a bit like winning the argument by giving up the reason you were arguing in the first place. For 3 decades, this all remained, in a very real sense, unresolved and untestable philosophy dressed up in physics clothing. And then, in 1964, working quietly at CERN, the great European particle physics laboratory near Geneva, an Irish physicist named John Stuart Bell did something that nobody had quite managed to do before. Bell was, by most descriptions, a careful, patient, somewhat private man, the sort of physicist who thought slowly and methodically rather than in flashes of dramatic insight, and who had actually been quietly turning the EPR argument over in his mind for years, almost as a private hobby, alongside his day-to-day work on particle accelerator theory, which was his official job at CERN. He asked a question so simple, so cleanly framed, that it's almost startling nobody had asked it quite that way in the previous 30 years. Bell asked, is there actually an experimental difference between what standard quantum mechanics predicts and what any possible local hidden variables theory could predict? Not a philosophical difference. An actual, measurable, numerical difference you could go check in a lab. And astonishingly, the answer turned out to be yes. Let me try to give you the intuition behind what Bell discovered, because the actual mathematics involves some careful statistics, but the underlying idea is something you can hold on to quite comfortably even as your eyes start to feel heavy. Imagine you're measuring the spin, or in real experiments, more often the polarization of entangled particles, but let's stick with spin for simplicity, along several different possible axes, not just one. Maybe you choose one of 3 different angles to measure at, chosen independently and randomly for each particle in the pair, right before the measurement happens. If Einstein's picture is correct, if each particle secretly carries a full, definite set of hidden properties along with it from the moment it was created, properties that determine what result you'd get no matter which angle you happen to choose to measure, then there's a mathematical ceiling, a hard limit, on how strongly correlated your measurement results can possibly be when you compare notes afterward across many different angle combinations. Bell worked out exactly what that ceiling is. It's now called Bell's inequality, and you can think of it a bit like a speed limit. If the universe is built the way Einstein hoped, local, with real hidden properties determined in advance, then the statistical correlations between distant measurements simply cannot exceed this particular value. It's a hard mathematical boundary, not a guess, not an approximation, a genuine ceiling derived from the assumption of locality plus hidden variables together. Here's a small, homely way to hold onto the shape of that idea, even if the real mathematics is more careful than this. Imagine each of our 2 entangled particles secretly carries a little instruction card with it, prepared back at the moment they were created together, telling it exactly how to respond, up or down, no matter which of the three possible angles someone later chooses to measure it at. If that's really how the universe works, then however you write those instruction cards, however cleverly you try to correlate the two cards with each other, there's only so far you can push the agreement between distant measurement results once you average over many different combinations of angles. It's a bit like two friends agreeing in advance on how they'll each answer three different yes or no questions, without being able to talk to each other again once the questions start being asked at random. However cleverly they plan their answers ahead of time, there's a limit to how consistently their answers can end up matching across all the different combinations of questions once you're comparing many rounds together rather than just one. Bell worked out precisely what the limit is for the entangled particle version of this game, and that limit is the inequality that carries his name. A few years later, in 1969, a group of four American physicists, John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, reworked Bell's original mathematics into a version that was much more practical to actually test in a real laboratory with real, imperfect equipment, and that reworked version, now usually called the CHSH inequality after their four initials, is the one most modern experiments, including the ones we're about to talk about, actually use. But quantum mechanics predicts something different. It predicts that under the right experimental setup, with entangled particles measured at cleverly chosen angles, the correlations will be stronger than that ceiling allows. Not infinitely stronger, not by some enormous margin that would be obvious to anyone, but definitely, measurably, mathematically stronger than any local hidden variables theory could ever produce, no matter how clever or complicated you try to make it. This was an enormous moment, even though almost nobody noticed it at the time. For the first time since 1935, the argument between Einstein and Bohr had stopped being a matter of philosophical taste and had become something you could actually go test with real equipment, real photons, real detectors, and real statistics. You could go into a lab, generate a whole lot of entangled particle pairs, measure them at carefully chosen angles, tally up thousands upon thousands of results, and simply check. Does the world stay under Bell's ceiling, the way Einstein's picture demanded? Or does it break through, the way quantum mechanics predicted? It took a little while for the experimental technology to catch up to Bell's theoretical challenge, but starting in the early 1970s, physicists began attempting exactly this kind of test. The very first serious attempt came in 1972, when John Clauser and Stuart Friedman, working at Berkeley, built an apparatus using entangled photons emitted from calcium atoms and found results that leaned toward quantum mechanics, violating a version of Bell's inequality, though with enough experimental uncertainty and enough unclosed loopholes that the results, while encouraging, didn't fully settle the question for the wider physics community. It was a promising first step rather than a final word, the sort of early result that tells you you're probably onto something real, while also making clear how much more careful work remains to be done. That much more careful work came in the early 1980s, carried out by a French physicist named Alain Aspect and his team at the University of Paris-Sud, in the town of Orsay, just outside the city. Aspect's experiments were genuinely ingenious, and it's worth understanding a little of why, because the cleverness here is exactly what closes the door on some of the more subtle ways Einstein's picture might have tried to sneak back in. He used pairs of entangled photons, generated by exciting calcium atoms in a very particular way, so that they'd emit two photons in quick succession, correlated with each other by the physics of the emission process. He sent these photon pairs flying off in opposite directions toward two separate detectors, each equipped with a device that could measure the photon's polarization, which is roughly analogous to the spin measurement we talked about earlier, along a chosen angle. And here's the crucial trick. Aspect built his apparatus so that the choice of which angle to measure at, on each side, could be switched extremely rapidly, while the photons were still in flight, still traveling through the apparatus toward the detectors. This mattered enormously, because it closed off a sneaky possible loophole. If the measurement angles had been fixed in advance, in principle, some kind of signal, even one traveling at the speed of light, could have passed between the two measurement stations before the photons arrived, somehow coordinating the results in a way that mimicked quantum entanglement without actually requiring anything spooky. By switching the settings after the photons were already on their way, faster than light could possibly travel between the two detection points. Aspect made sure that no such signal, however subtle, could have snuck through. And the results, when he tallied them up, were unambiguous. Bell's inequality was violated. The correlations Aspect measured were stronger than any local hidden variables theory could possibly explain, and they matched, quite precisely, what standard quantum mechanics had predicted all along. Einstein's hope that hidden properties determined in advance, combined with strict locality, could explain the strange correlations of entangled particles, was experimentally ruled out. Not proven philosophically inconvenient. Ruled out, tested against reality, and found wanting. Now, I want to be really careful and precise here, because this is exactly the kind of place where it's easy to oversimplify, and I don't want to leave you with a tidier story than the truth actually supports. What Bell's theorem and Aspect's experiments rule out, specifically, is the combination of locality and hidden variables together. That's an important distinction, and it's the reason David Bohm's pilot wave theory, the one we mentioned a moment ago, is still alive and well today, still taken seriously by a community of working physicists. Bohm's theory keeps hidden variables. Particles really do have definite positions and properties at all times in his framework. But it pays for that by abandoning locality outright, by building instantaneous, faster-than-light influence directly into its mathematical foundations. So you're allowed to keep hidden variables if you're willing to give up strict locality. Or, alternatively, you can keep locality, the way the Copenhagen interpretation does, but then you have to give up the idea of hidden variables, accepting instead that measurement genuinely creates definite outcomes rather than merely revealing pre-existing ones. What you cannot do, what Bell's work and decades of increasingly careful experiments have shown you simply cannot do, is have both local and deterministic hidden variables together, the specific combination Einstein was hoping for. That particular door has been closed. There is, in fairness, one more theoretical escape hatch that a small number of physicists and philosophers still discuss, usually called superdeterminism, and intellectual honesty requires at least a mention of it before we move on. The whole argument for Bell's inequality quietly assumes that the experimenters are genuinely free to choose which measurement angle to use on each run, independent of whatever hidden properties the particles happen to be carrying. Superdeterminism suggests that maybe that assumption is where the trouble lies, that perhaps the entire universe, including the supposedly random choices made by the physicists doing the choosing, was already fully determined from the very beginning of time, in a way that secretly correlates the experimenter's choices with the particle's properties, without either party ever being aware of it. It's a logically consistent way to preserve local realism, and it hasn't been experimentally ruled out, largely because it's built to be almost impossible to test, even in principle. But it comes at a genuinely enormous philosophical cost, giving up the idea that experimenters have any meaningful freedom in choosing their experiments at all, and treating the entire history of scientific inquiry as a kind of grand, pre-scripted coincidence. Very few working physicists find that trade worth making, but it's honest to note the door isn't quite welded shut, only left ajar in a way that most people studying it don't find remotely appealing to walk through. Even after Aspect's landmark results, a small number of careful, skeptical physicists kept pointing out that a couple of narrow theoretical escape hatches remained technically open, not because anyone seriously doubted quantum mechanics anymore, but because good science demands you close every last door before declaring a question fully settled. One was called the detection loophole, the worry that if your detectors only ever catch a fraction of the entangled particles you produce, maybe the particles you happen to detect aren't a fair, representative sample of all of them, and maybe that unfairness could somehow mimic a Bell violation without any real spookiness involved. The other was called the locality loophole, closely related to what Aspect's rapid switching had already addressed, the worry that some faster-than-light but still finite signal might sneak between the two measurement stations if the timing wasn't handled with total rigor. Over the following decades, various experiments closed one loophole or the other, one at a time, but closing every single loophole simultaneously, in one single, unimpeachable experiment, proved to be a genuinely difficult engineering challenge in its own right. The experimental confirmations have only grown more precise and more airtight in the decades since Aspect's original work. In 2015, a team led by the Dutch physicist Ronald Hansen working at Delft University of Technology in the Netherlands, carried out what's widely considered the first truly loophole-free Bell test, closing essentially every conceivable experimental gap simultaneously, using entangled electrons trapped in tiny diamond crystals located over a kilometer apart from each other. And the result was, once again, exactly what quantum mechanics predicted. Nature really does behave this strangely. This isn't an artifact of imperfect measurement or a subtle experimental error waiting to be discovered. It's simply how the universe is put together at its most fundamental level. And here's something worth pausing on for just a moment. Something quietly poignant if you let yourself sit with it. Einstein died in 1955. That's 9 full years before Bell even published his theorem, and decades before Aspect and Hansen and the others ran the experiments that finally, definitively answered the question Einstein had spent so much of his later career agonizing over. He never got to see it resolved. The man who essentially started this entire chapter of physics, who wrote the paper that made Schrödinger coin the word entanglement in the first place, who spent nearly the last 20 years of his working life convinced that the universe simply couldn't be as strange as quantum mechanics claimed, never lived to learn that the universe, in this particular argument, sided decisively with Bohr. But I don't think this story is really about declaring winners and losers, and I don't want you to drift off tonight thinking of it that way. Einstein was wrong about local hidden variables. That part is now about as settled as anything in experimental physics gets. But the questions he raised, the sharp, uncomfortable, beautifully precise questions in that 1935 paper, turned out to matter enormously, just not in the way he expected. Entanglement isn't some embarrassing loose thread in quantum theory that physicists have learned to quietly ignore. It's become a physical resource, something you can actually use, something engineers are building real machines around right now. Tonight, in laboratories and research facilities scattered across the world. The very thing Einstein dismissed as spooky, as surely a sign that something was missing from the theory, has become one of the most actively and productively exploited phenomena in all of modern physics. In a strange, almost beautiful irony, Einstein's greatest objection to quantum mechanics ended up illuminating some of its most powerful and most useful applications. Before we get to those applications, though, there's something important we need to clear up, something that tends to nag at people once they first hear about entanglement, and I want to get it fully settled before we go any further, so it doesn't sit uneasily in your mind while the rest of these ideas settle in around it. Here's the misconception, and it's an extremely natural one to have. If measuring one entangled particle instantly tells you something about its distant partner, doesn't that mean you could use entanglement to send messages faster than light? Couldn't you, say, encode information by choosing which property to measure, and have your partner on the other end somehow read that choice off their particle instantaneously? The answer is no, and it's worth understanding exactly why, because the reasoning here is elegant, and it should put your mind fully at ease. Think back to our two entangled particles, correlated so that if one comes up spin up, the other will always come up spin down along the same measurement axis. When you measure your particle and get spin up, you do learn, instantly, that your distant partner's particle, if measured along that same axis, will show spin down. That part is real. But here's the crucial piece. You had absolutely no control over which result you got. Your measurement came out spin up or spin down with a certain probability, essentially at random, and there was nothing you could do to force it one way or the other. You can't choose to make your particle come up spin up on command. So while you do learn something instantly about your partner's particle, you can't use that fact to send any actual information, because you never had any message to encode in the first place. It's a bit like flipping one of our match coins from earlier. Knowing that your friend's coin landed opposite to yours the instant you look at your own is genuinely fascinating, but you can't use it to send your friend a message because you never controlled what your own coin was going to show. Here's one more way to feel the shape of this, because it's worth being really settled on before we move any further. Suppose you tried to get clever about it. Suppose you decided that instead of measuring randomly, you deliberately choose which of several different properties to measure on your particle, hoping that your choice itself might somehow encode a message, a kind of Morse code written in your choice of measurement rather than in the outcome. Your distant partner, on their end, has no way whatsoever to tell, just from looking at their own particle, which property you happen to choose to measure on yours. All they can see, on their own end, is a string of individually random-looking results. It's only when the two of you later compare notes over an ordinary channel, no faster than light, that the remarkable correlation between your choices and their results becomes visible at all. Before that comparison happens, your partner's data looks like plain, unremarkable noise, indistinguishable from what they'd have seen if there were no entanglement at all. The pattern, the meaningful part, only exists in the relationship between two sets of data sitting in two different places, and you need an ordinary, speed-of-light-limited channel to bring those two data sets together before the pattern means anything at all. There's an even more formal way physicists express this, called the no-communication theorem, and it's one of the most solid, thoroughly proven results in all of quantum theory. It shows, with full mathematical rigor, that no matter how cleverly you try to set up an entanglement-based scheme, no matter what measurements you choose or how you try to manipulate your particle, there is no way to transmit usable information to your distant partner faster than a conventional signal, traveling at or below the speed of light, could carry that same information. The correlations between entangled particles are real, are instantaneous in a certain formal sense, and are also, somehow, completely useless for sending an actual message on their own. This isn't a technological limitation waiting for someone clever to find a workaround. It's baked into the deep structure of the theory itself, a genuine, permanent feature of how the universe works, not a bug that better engineering might one day fix. So hold that thought gently as we move forward tonight. Entanglement is real. It's spooky in exactly the sense Einstein complained about, and it absolutely cannot be used, on its own, to send a signal faster than light. Keep both of those facts sitting comfortably together, because we're about to see how this strange, communication-proof correlation becomes, instead, one of the most powerful tools ever discovered for doing things that have nothing at all to do with faster-than-light messaging, and everything to do with security, precision, and computation. Let's turn now, gently, from the philosophy of what entanglement means to the engineering of what entanglement does. Because somewhere along the long, quiet decades between Einstein's original objection and today, entanglement stopped being a purely philosophical curiosity and became fuel, a genuine physical resource that clever people have learned to harness. The first place this really shows up in a way you can touch, in a way that already protects real information moving across the real world right now, is quantum cryptography, and specifically something called quantum key distribution. Here's the underlying idea, and it's really quite elegant once you see it laid out. Imagine two people, let's just call them, the way cryptographers traditionally do, Alice and Bob, who want to share a secret encryption key, a string of random numbers they can both use to scramble and unscramble their messages, without anyone eavesdropping being able to learn what that key is. In ordinary, non-quantum cryptography, this is a surprisingly hard problem, because any signal you send to share the key could, in principle, be intercepted and copied without either Alice or Bob ever noticing. Quantum mechanics offers something genuinely new here, something that has no classical equivalent whatsoever. If Alice and Bob use entangled particles, or in some schemes, individual quantum particles prepared in particular delicate states, to establish their shared key, then the very act of an eavesdropper trying to intercept and read those particles necessarily disturbs them, in a way that Alice and Bob can detect afterward. This isn't a matter of building better locks. It's a direct, physical consequence of a deep principle sometimes described through Heisenberg's uncertainty, the same kind of principle that says you cannot measure certain properties of a quantum system without inevitably disturbing others. The very first practical scheme for putting this idea to work was worked out in 1984 by Charles Bennett, the same physicist we're about to meet again in a few minutes in connection with quantum teleportation, together with Gilles Broussard, and it's usually just called BB-84, after their initials and the year. In BB-84, Alice sends Bob a stream of individual photons, each one prepared in one of two possible ways of encoding a 0 or a 1, using two different, incompatible measurement bases, chosen at random for each photon, without telling Bob in advance which basis she used for which photon. Bob measures each incoming photon using his own randomly chosen basis, again without knowing ahead of time whether he's guessed the same basis Alice used. Afterward, over an ordinary public channel, They compare notes about which basis each of them happened to use for each photon. Not the actual results, just which basis, and they simply throw away the results from any photon where their bases didn't match. What's left? The results from photons where they happen to choose matching bases becomes their shared secret key. And crucially, if an eavesdropper had tried to intercept and measure any of those photons along the way, guessing at the basis just as Bob had to, they'd inevitably guess wrong a certain fraction of the time, and that wrong guess disturbs the photon in a way that shows up later as extra errors when Alice and Bob compare a sample of their results. Real quantum key distribution networks running today, in places like Beijing, Vienna, and several other cities around the world, still lean on this same essential logic, refined and engineered considerably, but built on exactly this foundation. China, in particular, has built out a backbone connecting Beijing and Shanghai, stretching over 2,000 kilometers, relaying quantum keys through a chain of trusted intermediate stations along the way, and has used it to protect certain especially sensitive government and financial communications. Banks in several countries have experimented with quantum-secured links between data centers, and a handful of national research networks in Europe now route at least some portion of their most sensitive traffic through quantum-protected connections. None of this has replaced ordinary encryption for everyday use. Not yet, and probably not for a good while longer, since the equipment remains expensive and the distances it can cover without a trusted relay remain limited. But it's no longer purely theoretical. It's quietly, steadily becoming infrastructure. An eavesdropper simply cannot look at a quantum message in transit without leaving fingerprints, without introducing detectable errors into the correlations Alice and Bob are relying on. So instead of trying to make eavesdropping impossible, quantum key distribution makes eavesdropping detectable every single time, as a matter of physical law rather than mere engineering. Alice and Bob compare a portion of their results afterward, over an ordinary, insecure classical channel, and if the error rate is too high, they know someone was listening, and they simply throw away that batch of key material and try again. If the error rate stays low, they know, with mathematical certainty rooted in physics rather than assumption, that their shared key is genuinely secret. This isn't science fiction. Quantum key distribution networks already exist and are already being used today to protect certain especially sensitive communications, stretching across metropolitan fiber optic networks and, as we'll see in a few minutes, even reaching all the way up into orbit. The second major application, and one that tends to sound the most like something out of a story when you first hear it described, is quantum teleportation. And I want to be very careful here, because the word teleportation carries a lot of baggage from science fiction. Images of a person dissolving in one place and reassembling somewhere else, and that is absolutely not what's happening. What gets teleported in quantum teleportation is information, specifically the precise quantum state of a particle, not any physical matter at all. Bob's particle was already sitting there in his laboratory the whole time, a perfectly ordinary particle in its own right. What teleportation does is take the delicate, unknown quantum information that was originally written onto Alice's particle and transfer it, completely and exactly, onto Bob's particle instead, while erasing it from Alice's particle in the process. Nothing physical travels between them at all except an ordinary, classical message telling Bob how to finish the job. It might be more accurate, if considerably less catchy, to call it quantum state transfer, but teleportation is the name that stuck back in 1993, and by now it's far too late to change it. Here's how it works, in outline. Developed originally in 1993 by a physicist named Charles Bennett along with several collaborators. Suppose Alice has a particle in some particular, possibly quite delicate and unknown quantum state, and she wants to transfer that exact state to Bob, who might be far away. She and Bob share a pair of entangled particles between them, prepared in advance. Alice performs a particular joint measurement involving both her original particle and her half of the entangled pair, a measurement that, in a certain technical sense, mixes the information from both together. This measurement necessarily destroys the original state on Alice's end, so nothing is being duplicated here. No violation of the deep principle in quantum mechanics that says you cannot make a perfect copy of an unknown quantum state. Alice's measurement produces one of several possible outcomes, essentially at random, and depending on which outcome she gets, Bob's particle, thanks to its entanglement with Alice's, ends up in a state closely related to the original, but not quite identical to it, distorted in a specific, predictable way depending on which outcome Alice got. Here's the crucial part, the part that keeps this whole process safely inside the boundaries of the no communication theorem we talked about a few minutes ago. Alice has to tell Bob, over an ordinary classical communication channel, radio waves, a fiber optic cable, a phone call, it doesn't matter which of her possible measurement outcomes she actually got. And once Bob knows that, he can apply a simple, specific correction to his particle, and voila, his particle ends up in exactly the same state Alice's original particle was in. The information has been teleported. But notice, Bob had to wait for that classical message to arrive, traveling no faster than light, before he could complete the process and actually recover the state. So even quantum teleportation, for all its evocative name, respects the speed limit built into the universe. It's faster-than-light information transfer only in a very narrow, specific sense, and completely useless for sending an actual message any faster than an ordinary signal could carry it. Charles Bennett developed this protocol together with a small group of collaborators, including Gilles Broussard again, along with Claude Crepeau, Richard Jossa, Asher Perez, and William Wouters, publishing their work in 1993, and it caused a considerable stir precisely because the word teleportation had always belonged to science fiction before that. And here, suddenly, was a rigorous, mathematically airtight protocol that actually deserved the name, at least for information rather than matter. The very first experimental demonstrations, teleporting the state of an actual photon across a laboratory bench, came just a few years later, in 1997, from two independent teams, one led by Anton Zeilinger in Innsbruck, Austria, and another led by Francesco de Martini in Rome. Since then, the distances involved have grown steadily and, in places, almost dramatically. Teleportation has been demonstrated across many kilometers of optical fiber running under real cities, across open air between mountaintop laboratories in the Canary Islands separated by over 100 kilometers, and, remarkably, between a ground station and an orbiting satellite. Which brings us to one of the single most vivid, most concrete images in this entire story, something that happened not so very long ago, in 2016 and 2017. China launched a satellite called Mischius, named after an ancient Chinese philosopher and engineer from around the 5th century BCE, who is sometimes credited with some of the earliest recorded experiments involving light and optics, a nod that feels quite fitting for a mission built entirely around beams of photons. The project was led by the physicist Pan Jianwei, sometimes described in the press as the father of China's quantum satellite program. And the satellite itself was purpose-built with an onboard crystal capable of generating pairs of entangled photons, and then carefully aiming one photon from each pair down toward one ground station, while aiming its twin down toward a completely separate ground station, using precision tracking optics to compensate for the satellite's own rapid motion across the sky. Think about what that actually means for a moment. A satellite, orbiting hundreds of kilometers above the Earth, creating pairs of entangled photons, and sending one member of each pair down through the atmosphere to one location, and the other member down through the atmosphere to a completely different location, over 1,000 kilometers away, and the entanglement survives the whole journey. It survives passing through Earth's turbulent, scattering, absorbing atmosphere, survives traveling those vast distances, and remains intact and measurable when it finally arrives. The photons still show those same Bell-violating correlations that Aspect first demonstrated back in a small laboratory in France in the early 1980s, except now stretched clear across a continent, bounced off a satellite in orbit. It's a genuinely beautiful, almost cinematic image to hold in your mind. Entanglement, this delicate, philosophically troubling correlation that Einstein found so uncomfortable he spent decades trying to explain it away, now literally beaming down from space, forming the backbone of real quantum communication experiments. Let's turn, gently, to the application of entanglement that gets talked about the most these days, the one you've most likely heard mentioned in the news at some point: quantum computing. The seed of this whole idea is usually traced back to a talk given in 1981 by the physicist Richard Feynman, a wonderfully colorful character in his own right, at a conference held at MIT. Feynman made an observation that sounds almost obvious once you hear it, though nobody had really taken it seriously before him. If nature itself, he pointed out, is fundamentally quantum mechanical at its core, full of superpositions and entanglement and probability, then trying to simulate nature using an ordinary classical computer is bound to be hopelessly inefficient, because a classical machine has to separately track every single possible quantum state of the system you're simulating. And the number of those states grows exponentially larger with every additional particle you add. But, Feynman suggested, a computer that itself ran on quantum principles, one that could hold superpositions and entanglement the way nature does, might be able to simulate these systems naturally, efficiently, almost effortlessly by comparison. He wasn't proposing a specific design, just pointing toward a horizon and saying, essentially, there's something important sitting over there. A few years later, in 1985, a physicist named David Deutsch at Oxford took that vague pointing gesture and turned it into rigorous mathematics, describing what a genuinely universal quantum computer would actually look like, laying the theoretical groundwork that the whole field has built on ever since. Here's something worth clearing up first, because it's a common point of confusion. Superposition alone, that idea we talked about earlier, of a particle existing in a smeared-out combination of possibilities until measured, isn't actually enough, by itself, to give a quantum computer its real power. You need entanglement too. Superposition lets a single quantum bit, or qubit, hold a combination of both 0 and 1 simultaneously, rather than being locked into just one value the way an ordinary classical bit is. That's already interesting, but it's entanglement that lets you link many qubits together into a single, unified quantum state, so that the whole collection of qubits can represent and manipulate an absolutely staggering number of possibilities all at once, growing exponentially with each additional qubit you add. A modest handful of entangled qubits, arranged and manipulated the right way, can represent more distinct combinations of information than there are atoms in your body. That's the real source of a quantum computer's potential power. It's the entanglement between the qubits, not merely the superposition within each one individually, that lets certain carefully designed calculations explore vast landscapes of possibility all at once, in ways no ordinary classical computer, however large or fast, could ever hope to match for particular kinds of problems. This connects, in a lovely full-circle way, right back to the threat that quantum key distribution is designed to defend against in the first place. There's a famous algorithm, developed by a mathematician named Peter Shor, working at Bell Labs, back in 1994, that shows how a sufficiently powerful quantum computer could, in principle, factor extremely large numbers exponentially faster than any known method running on an ordinary classical computer. It's worth pausing on why that particular mathematical trick matters so enormously. Most of today's encryption, the kind protecting your bank transactions, your emails, all sorts of sensitive digital communication, rests on a rather elegant assumption that while it's easy to multiply two very large prime numbers together to get an even larger number, it's fantastically, prohibitively difficult to go the other way. To take that large number and figure out which two primes were originally multiplied together to produce it. Ordinary computers, however powerful, would need an impractical amount of time, sometimes longer than the age of the universe, to factor a sufficiently large number this way. Shor's algorithm showed, entirely on paper at first, that a quantum computer exploiting entanglement between its qubits could solve this same factoring problem in a dramatically shorter time, undermining the whole foundation that this kind of encryption rests on. This is exactly why the quantum key distribution networks we talked about a few minutes ago matter so much for the future, and why governments and standards organizations have already begun rolling out newer forms of encryption, sometimes called post-quantum cryptography, designed around different mathematical problems that even a quantum computer wouldn't have an easy shortcut for. They're built on physical principles, on the actual behavior of entangled particles, rather than on the assumed mathematical difficulty of factoring. And physical principles like these are not something a more powerful quantum computer could ever come along and simply outrun. Building a real, working quantum computer that can hold on to entanglement long enough to actually do something useful with it turns out to be extraordinarily difficult, and it's worth understanding just a little bit of why, because the challenge itself is instructive. Entangled quantum states are wonderfully delicate. The tiniest interaction with the surrounding environment, a stray vibration, a stray photon, even just a small fluctuation in temperature, can cause the entanglement to fall apart, a process called decoherence, in which the pristine quantum correlations blur into ordinary, boring classical randomness. This is precisely why so many quantum computers you might have read about operate at temperatures colder than the depths of outer space, just a tiny fraction of a degree above absolute zero, held inside elaborate refrigeration systems, all in an effort to slow down that inevitable process of decoherence long enough to actually finish a calculation. There are several quite different physical approaches researchers are pursuing to actually build these entangled qubits, and it's worth knowing the names even briefly, because you'll likely come across them again. Some companies, like Google and IBM, build their qubits out of tiny superconducting electrical circuits, cooled down to a whisper above absolute zero, where electrical current can flow in a delicate quantum superposition of two directions at once. Others, like the companies IonQ and Quantinuum, trap individual charged atoms, ions, suspended in space using oscillating electric fields, and manipulate their internal energy states with precisely tuned laser beams, entangling neighboring ions through their shared physical vibrations. Each approach has its own strengths and its own stubborn engineering headaches, and it's genuinely still an open question which approach, or which combination of approaches, will ultimately prove most practical for building large, reliable machines. And when you need one reliable, well-behaved logical qubit for an actual calculation, you often need to combine the efforts of many, many imperfect physical qubits, all working together through a clever technique called quantum error correction. The idea there is subtle and worth pausing on for a moment, because it connects directly back to something we talked about earlier. In ordinary classical computing, if you're worried a bit might flip by mistake, you can simply make several copies of it and take a majority vote if something goes wrong. But remember, you cannot make a perfect copy of an unknown quantum state. That's the same principle underlying why quantum teleportation has to work the roundabout way it does. So instead of copying, quantum error correction spreads a single logical qubit's information out across many entangled physical qubits, in a way that lets you detect and fix certain kinds of errors without ever directly looking at, and thereby collapsing, the delicate quantum information you're trying to protect. It's a genuinely elegant trick, and it's entanglement itself that makes it possible. Right now, in this particular moment, the field sits in what researchers sometimes call the noisy intermediate-scale quantum era, a slightly clunky name for a genuinely fascinating in-between period. The machines that exist today, built by companies like Google and IBM among others, have real, working qubits, sometimes numbering in the dozens, sometimes in the hundreds or more, genuinely entangled with each other and capable of carrying out calculations no ordinary computer could easily reproduce. In 2019, Google announced that a processor of theirs, containing 53 superconducting qubits, had completed a very specific, carefully chosen calculation in about 200 seconds, a calculation the company's engineers estimated would take the most powerful classical supercomputers on Earth many thousands of years to reproduce, a claim they called quantum supremacy. Researchers at IBM pushed back on some of the details, arguing that with sufficiently clever classical techniques, the same calculation might be done considerably faster than Google had estimated. And that particular friendly, technical disagreement over the exact numbers has continued in the years since. But the broader trajectory isn't really in dispute. These machines are real. They genuinely rely on entangling many qubits together to do what they do. And the errors that still plague them, the noise and noisy intermediate-scale quantum, are exactly the kind of decoherence we've been talking about all along. The same fragile entanglement falling apart under the gentlest disturbance from the surrounding world. Nobody sensible expects a quantum computer to replace the laptop or phone you use for ordinary tasks. They're specialists, extraordinarily good at a narrow slice of problems with just the right mathematical shape, drug discovery, new battery chemistries, certain kinds of optimization and cryptography, rather than general-purpose machines for everyday life. And beyond quantum cryptography, beyond quantum teleportation, beyond quantum computing, there's a further dream, one that researchers are actively working toward right now. sometimes called the quantum internet. The basic idea is to build a global network capable of distributing entanglement between distant locations reliably, the way the Michias satellite did on an experimental basis, but routinely, robustly, everywhere. This would let far-flung quantum computers link up and work together, would let quantum key distribution stretch seamlessly across continents rather than just individual metropolitan networks, and might enable forms of extraordinarily precise, distributed scientific measurement that simply aren't possible any other way. One of the central engineering challenges standing in the way is something called quantum repeaters. In ordinary fiber optic communication, if a signal weakens too much over a long distance, you can just amplify it, boost it back up, and send it on its way. But you cannot simply amplify a fragile quantum state the way you'd amplify an ordinary optical signal, again because of that same deep principle against copying unknown quantum information. So researchers are developing quantum repeaters instead, clever devices that use additional entanglement, in a process sometimes called entanglement swapping, to effectively extend the reach of quantum correlations across much longer distances than would otherwise be possible, one careful link at a time. Entanglement swapping itself is a lovely piece of physics in its own right, and it's worth taking just a moment to picture how it works, because it's essentially the same trick underlying quantum teleportation, applied in a slightly different way. Imagine two separate pairs of entangled particles. One pair has a particle sitting at station A and a particle sitting at station B, roughly halfway along a long chain. The second pair has a particle sitting at that same halfway station B and a particle sitting further along at station C. Neither of the particles at station A and station C has ever interacted with the other directly, and they aren't entangled with each other, not yet. But if you perform a particular joint measurement on the two particles that happen to be sitting together at station B, something remarkable happens. The entanglement effectively swaps, or teleports, so that the particle way back at station A and the particle way out at station C become entangled with each other instead, even though they've never been anywhere near one another. Chain enough of these swaps together, station after station, and you can, in principle, extend entanglement across distances far greater than any single link could survive on its own, weaving together a network the way relay stations once let a signal fire travel across an entire mountain range, one beacon at a time, without any single beacon needing to see the whole distance itself. This is very much an active area of research right now, not yet a finished, deployed technology, but the theoretical groundwork and the early experimental demonstrations are already there, quietly accumulating, the way most transformative technologies do, long before anyone outside the field notices. There's one more corner of this story worth pausing on gently before we start to widen our view again, because it's genuinely wonder-inducing, even though I want to be careful to flag it honestly as speculative, still very much debated among scientists, rather than settled fact the way the Bell test experiments are. Some researchers have wondered whether entanglement, or something closely related to it, might play a functional role even inside living things. There's an active area of study looking at whether certain biological processes, like the astonishingly efficient way plants and some bacteria capture and funnel the energy of sunlight during photosynthesis, might rely on a kind of quantum coherence between different molecular pathways within the light-harvesting complexes inside their cells, letting the captured energy explore multiple possible routes toward the reaction center simultaneously, sampling many paths at once before settling into the single most efficient one, rather than stumbling along a single random path the way an ordinary classical description would suggest. Some careful experiments, involving ultra-fast laser pulses and cooled samples, have reported signatures consistent with this kind of coherence lasting for a surprisingly long time, given how warm and messy a living cell is, though other researchers have pushed back, arguing that at true biological temperatures the effect may be far more fleeting or ambiguous than the earliest, more dramatic headlines suggested. It remains a genuinely open, actively debated question. There's also a genuinely fascinating, still quite contested hypothesis about certain migratory birds, the kind that manage to navigate thousands of miles across open ocean and unfamiliar continents with an accuracy that still isn't fully explained. The idea, sometimes called the radical pair mechanism, suggests that a light-sensitive protein inside a bird's eye, when struck by a photon, can produce a pair of electrons whose combined quantum state briefly becomes entangled, and that the surrounding Earth's magnetic field, oriented differently depending on the bird's heading, subtly influences how that entangled pair evolves before it settles into one chemical outcome or another. If this hypothesis holds up, the bird would, in a very real sense, be seeing the planet's magnetic field lines as part of its visual experience, using entanglement as a built-in compass. Neither of these ideas, the photosynthesis story or the bird story, has anywhere near the rock-solid experimental confirmation that Bell's theorem or the Aspect and Hansen experiments have. They remain active, contested, exciting frontiers of research, the kind of thing where new results come out every year and the picture keeps shifting. But it's a lovely thought to let drift through your mind for a moment anyway. The possibility that this strange correlation Einstein found so troubling might be quietly at work, not just in satellites and cryptography networks, but perhaps, in some small way, inside the leaves outside your window, or inside the tiny brain of a bird finding its way home across a continent. Now, having spent all this time on what entanglement does, I think it's worth pulling back, gently, and asking what it actually means, because physicists themselves, even now, nearly a century after Einstein and Podolsky and Rosen wrote their famous paper, don't fully agree on the answer. Here's the honest, even-handed truth of where things stand. The mathematics of quantum mechanics is not in dispute. Every single experiment, going back through Aspect in the 1980s all the way to Hansen's loophole-free tests in 2015 and beyond, confirms the predictions of the theory with extraordinary precision, again and again, without exception. But the question of what that mathematics is actually telling us about the deep nature of reality, what's really happening underneath the equations, remains a subject of genuine, ongoing, good-faith disagreement among serious physicists and philosophers of science. The Copenhagen interpretation, the view that measurement genuinely creates definite outcomes rather than merely revealing pre-existing ones, remains probably the most widely taught view, the default picture most physics students encounter first. But it's far from the only serious position. There's the many-worlds interpretation, proposed in 1957 by a young graduate student at Princeton named Hugh Everett, working, as it happens, in the very same physics department where Einstein himself was still occasionally seen walking the grounds in his final years. Everett's idea, worked out as his doctoral thesis, was that the wave function never actually collapses at all. Instead, every possible measurement outcome genuinely happens, each one branching off into its own separate, equally real version of the universe, so that after you measure our entangled pair, there isn't one universe where you got spin up and your partner got spin down. There are two entire branches of reality, one where that happened and one where the opposite happened, both equally real, neither one more true than the other, with the version of you reading each branch simply unaware that the other branch exists at all. It's a strange, almost vertiginous idea, and it was met with considerable indifference at the time, largely ignored for over a decade, until physicists like Bryce DeWitt picked it up again in the late 1960s and gave it the more evocative name it's known by today. Everett himself, discouraged by the muted early reception, left academic physics altogether not long after finishing his thesis and spent much of the rest of his career working on defense analysis and operations research instead, a quiet, somewhat melancholy footnote to an idea that would go on to become one of the most seriously discussed interpretations in all of modern physics. There's Bohm's pilot wave theory, which we already met, keeping hidden variables alive at the cost of strict locality. And there are other views too, like relational quantum mechanics, developed more recently by the Italian physicist Carlo Rovelli, which suggests that a quantum state isn't an absolute, universal fact at all, but always relative to whichever observer or system is doing the observing, so that asking what the real, observer-independent state of a particle is might be a bit like asking what the real, frame-independent speed of a car is, a question that quietly smuggles in an assumption the theory itself says isn't valid. Smart, serious, deeply knowledgeable people disagree passionately about which of these pictures, if any of them, is the right way to think about what's actually going on. And here's the thing I find genuinely reassuring about that disagreement, rather than unsettling. The math works, regardless of which interpretation you personally favor. The predictions are confirmed to a level of precision that borders on the absurd. Quantum electrodynamics, the theory built on these same foundational ideas, predicts a particular property of the electron called its magnetic moment to an accuracy of roughly 1 part in 10 trillion, an agreement between theory and experiment, so exact it's a little like predicting the distance from one side of a country to the other and getting it right to within the width of a single human hair. We know how to use this theory. We know how to build extraordinary things with it. We're still figuring out, all these decades later, exactly how to understand it in our bones, and maybe that's simply the honest, humble place where this particular story currently rests. So let's bring this gently back down to earth, back to the room you're lying in right now, and let the whole arc of tonight's story settle around you like a blanket. It started with 2 particles, born together, flung apart across some unimaginable distance, and yet somehow still bound together by a correlation deeper than the space between them. It moved through Schrödinger's cat, sealed in its box, alive and dead at once until someone dares to look, a thought experiment meant as a challenge that became an icon instead. It moved through Einstein, Podolsky, and Rosen, building their careful, elegant argument that the universe simply couldn't be as strange as it seemed to be, that some deeper, more comfortable layer of hidden reality must be waiting underneath. It moved through decades of quiet philosophical stalemate, argument without resolution, until a patient physicist at CERN named John Bell found a way to turn philosophy into something you could actually test. It moved through Alain Aspect's careful, clever experiments in France, switching measurement settings faster than light itself could cross the gap between his detectors, and found, unambiguously, that the universe sides with the strange picture, not the comfortable one. It moved through Einstein's own death, in 1955, 9 years before Bell even published the theorem that would have finally, definitively answered the question that haunted so much of Einstein's later life. And then it moved forward, out of pure philosophy entirely, into satellites beaming entangled photons down through the atmosphere, into cryptography networks that catch eavesdroppers not through clever code, but through the unbendable laws of physics itself, into quantum computers held colder than the space between the stars, patiently trying to hold on to entanglement long enough to compute something extraordinary, into the tentative, still-forming dream of a quantum internet stretching around the whole planet, and maybe, quietly, into the leaves outside your window, into the tiny compass hidden inside a bird's eye. We don't fully know yet. Some of the story is still being written, right now, by people awake in laboratories on the other side of the world from you while you drift towards sleep. There's one more thing I want to leave you with before we let this all settle, something that ties the whole night together in a way I think is genuinely comforting rather than unsettling. Entangled photons have existed since the very beginning of everything, since the earliest moments of the universe itself, back when the whole of what would become everything you can see was compressed into a space almost too small to imagine, hot and dense, and thoroughly quantum mechanical in its behavior. Correlations were being threaded through that primordial soup long before there was anyone around to notice them or to argue about what they meant, long before Einstein or Bohr or Schrödinger, long before there were stars to burn or planets to circle them, long before there was a you to lie here thinking about any of it. And inside your own body, right now, there are particles that are entangled with other particles, correlations woven through the very atoms that make you up, quietly there, doing whatever it is they do, whether or not anyone is thinking about them, whether or not anyone fully understands them yet. You don't feel it. You were never meant to. It happens at a scale so far beneath your conscious experience that it might as well be happening in another universe entirely. And yet it's happening inside the hand resting on the blanket, inside the slow rise and fall of your own breathing. There's an especially beautiful, understated example of entanglement being put to practical use in one of the most sensitive scientific instruments ever built, the LIGO Gravitational Wave Observatory, with its 2 enormous L-shaped detectors, each arm stretching 4 kilometers, one in the state of Washington and one in Louisiana, built to listen for ripples in the fabric of space-time itself, caused by things like 2 distant black holes spiraling into each other and colliding, sometimes over a billion light-years away. The ripple that reaches Earth from an event like that is almost unbelievably faint, capable of stretching and squeezing LIGO's 4-kilometer arms by a distance thousands of times smaller than the width of a single proton. To catch something that faint, you have to fight against every possible source of noise. And it turns out that even the fundamental uncertainty built into quantum mechanics itself shows up as a kind of noise floor. A limit on how precisely you can measure certain properties of the laser light LIGO depends on. In its more recent upgrades, LIGO actually uses specially prepared, squeezed states of entangled light where the uncertainty has been carefully redistributed, reduced in the one property the experiment actually cares about measuring precisely, at some cost to a different property nobody there is paying attention to, in order to push its sensitivity past what the ordinary limits of quantum uncertainty would otherwise allow. Its uncertainty being used, cleverly, gently, to beat itself. Entanglement enlisted as a quiet ally in the project of listening to the universe's oldest and most violent collisions. Entanglement, in other words, isn't just some far-off, abstract curiosity confined to laboratories and thought experiments. It's genuinely stitched into the operation of the universe at every scale, from the birth of the cosmos to black holes colliding a billion light-years away to the delicate machinery listening for their echo right here on Earth, to the quiet, unnoticed atoms making up the body you're resting in right now. So let that settle now, gently, the way the correlations themselves have been quietly settling into the fabric of everything since the very beginning. You don't need to hold on to all the details. You don't need to remember exactly how Bell's inequality works, or exactly what happened at Delft in 2015, or exactly how a quantum computer keeps its qubits entangled long enough to be useful. You don't need to remember Einstein's gloves, or Schrödinger's cat, or the name of a single satellite. None of that is the point of tonight. The point of tonight was simply to sit for a while with the fact that the universe is stranger, and somehow also more quietly, elegantly connected, than it lets on during the ordinary business of the day. Let your thoughts drift the way a photon's possibilities drift before anyone measures them, wide open, unresolved, in no rush at all to collapse into anything definite. There's no test at the end of this. There's no measurement waiting to force your thoughts into one tidy shape or another. You're allowed to stay soft and undetermined for a while, the way a particle is soft and undetermined before somebody insists on an answer. The universe has been running on these strange, beautiful correlations since long before you were born, and it will keep on running this way long after tonight, whether or not you're awake to think about it. Somewhere, entangled photons are still streaming down from a satellite toward 2 ground stations. Somewhere, a chain of cold, careful machines is still holding a fragile superposition together for one more fraction of a second. Somewhere, entangled light is still helping a giant detector listen for the echo of 2 black holes that collided long before the Earth even existed. None of it needs you to be awake for it. None of it needs you to understand it perfectly, or at all, for it to keep quietly, faithfully happening. So let your mind loosen. Let the ideas blur softly at the edges, the way 2 separate things blur into one shared, undetermined story when they're entangled. And whenever you're ready, let yourself drift off, gently entangled with nothing more demanding tonight than the quiet, unresolved comfort of sleep.